Hi friends, welcome back to Acharya Gurukulam. Today's topic is the key insights of the devastating March 28, 2025 Myanmar earthquake, a comprehensive overview. In this video, I am going to explain the seismotectonic features, seismological aspects, the ground motion analysis. In that ground motion analysis, time history records, Fourier amplitude spectrum and response spectrum, and finally the conclusions. The Earth is divided into 14 major tectonic plates and 40 minor tectonic plates. And the major tectonic plates are as follows. You can see the list of major tectonic plates. Antarctic plate having an area of 60 million kilometers square. North American plate having a area of 76 million kilometers square. South American plate having a area of 43 million kilometers square. Pacific plate having an area of 103 million kilometers square. India, Australia plate 58 million kilometers square. African plate 61 million kilometers square. Eurasian plate 67 million kilometers square. Among all the tectonic plates, the Pacific tectonic plate having a major area. And you can see the plate tectonics locating 1, 2, 3, 4, 5, 6 in this slide. And you can see the rates of the seismotectonic plates motion. The seismotectonic characteristics of the recent devastating Myanmar earthquake are predominantly influenced by the interaction between the Indian, Burmese and Sanda plate. So you can see here the Indian plate, Burmese plate and the Sanda plate. The substantial number of significant earthquakes have occurred along the boundary of these tectonic plates. The Sanda plate and a minor tectonic plate which is moving at a rate of 11 to 14 per year and is primarily located in the Southeast Asia. The Sanda megathrust fault starts from Myanmar in the north, runs along the southwest and terminates near the Australia. The interaction between the Indian and Sanda plate is most significant along the Sumatra Andaman subduction region. The Burmese plate lies along the oblique interaction eastern part of the Indian plate. Besides the Sanda plate, the interaction between the Indian and Burmese plate lead to high seismicity in the north and low seismicity in the south, as the Indian plate is subducting beneath the micro-Burmese plate at a dip angle of 18 to 25 degrees. Strike slip Sagaing fault is one of the major sources of the earthquake that runs through the major cities of Myanmar like Yangon, Naipida and Mandalay. The strike angles for all the segments ranges from 350 degrees to 358 degrees with a constant dip angle of 82 degrees. The 1500-kilometer long Sagaing strike slip fault originates from southeast Himalaya to northeast Andaman Sea, which is the boundary between Burma and Sanda plate, slide at a rate of 18 to 50 mm per year. It is one of the major sources of the earthquake runs through the major cities of Myanmar like Yangon, Naypyidaw and Mandalay. According to the previous studies, the Sagaing fault, you can see the Sagaing fault here. The Sagaing fault is typically divided into two primary regions, the northern and southern sections. Additionally, it is further subdivided into six segments. You can see here. So these are the six segments. Banmark, Sagaing, Maiktila, Naipada, Payo, and Bago. So you can see these are the segments that are there for the Sagaing fault. The strike angles for all the segments ranges from 350 degrees to 358 degrees with a constant dip angle of 82 degrees. Central Myanmar frequently experience moderate to strong earthquakes with 6 events of magnitude 7 or higher recorded between 1930 and 1956 along the fault or nearby structures. So you can see here the past earthquakes that occurred in the Myanmar region. A 70-kilometer long Naypyidaw segment is located beneath Naypyidaw, and the last earthquake recorded on the fault was in 1929 with a magnitude of 6.6. Another 220-kilometer length Maitila segment extended to Mandalay. The 1839 Awa earthquake of magnitude MW8 occurred on this fault. Another Sagaing segment that runs parallel to Irrawaddy River ruptured during the 1946 Sagaing earthquake, the 1956 Sagaing earthquake with a magnitude of 7.1, and the latest 2025 Myanmar earthquake with a magnitude of 7.7. The Sagaing fault, along with its associated parallel structures, plays a major role in accommodating the strike slip component of the region. Oblique plate converges. It exhibits a lateral slip rate of approximately 15 to 25 mm per year with a total displacement between 100 to 700 kilometers. Also, it accounts for nearly 50 to 55% of the total plate motions in the region. Unlike thrust faults, where seismic activity may originate at varying depths, earthquakes on strike slip fault tend to occur at relatively shallow depths, typically between 10 to 15 kilometers. A similar pattern was observed in Myanmar earthquake, which occurred at a shallow depth of 10 kilometers. One of the most insightful analysis involved calculating the cumulative Coulomb stress imparted by 10 significant seismic shocks with a magnitude more than 6.5 along the Sagaing fault since 1906. For the purpose of slip distribution across the strike slip fault, a finite fault inversion algorithm was used by USGS using waveforms. We can see here the slip distribution from south to the north. A total length of 530 kilometers fault is divided into 4 segments, and slip distribution of each segment is shown here from south to north. The rupture initiated at segment 1 with a maximum slip of 4.33 meters at Mandalay in the north and propagated southward. The rupture continued through the segments 2 and 3 with a maximum slip of 3.9 and 3.17 at Maitila and Ottara respectively. Finally, the rupture terminated at segment 4 where the maximum slip was 2.18 meters at Yadeshe in the south. Among the 4 segments, the maximum slip of 4.33 meter occurred at Mandalay, which is located near the epicenter. You can see here, this is the epicenter. This is the location of epicenter. Approximately 50% of the slip values fall between 1.5 meter to 3.2 meter, while about 25% of the slip values exceed 3.18 meter. The major 3 cities situated along the Sagaing fault, one is Sagaing, Mandalay, and Naipida, experienced a seismic intensity of 9 during the earthquake. Now you can see here the distribution of the distribution of the slip along the 4 segments of the Sagaing fault. This is S1 indicates the segment 1, segment 2, segment 3, and segment 4. And these are the maximum values along the segment. So according to the CES MD, that is the Center for Earthquake Strong Motion data, only 5 stations the earthquake was recorded. The seismic data from accelerographs in the Myanmar and Thailand region was monitored by a Myanmar National Seismic Network and the Global Seismograph Network. Ground motion time histories were recorded at 4 stations in Myanmar and Naipida, Guang and Yangon and Tunsha, and 1 station in Thailand, that is Chiang Mai. The Nuang and Naipida stations are located at the epicentral distances of 137 kilometers and 248 kilometers respectively, while the station in Thailand is situated at an epicentral distance of approximately 500 kilometers. And here the ground motion records acceleration, velocity, and displacement time history records are shown in this slide. The ground motion records were recorded at Naipida station, which is 248.4 kilometers from the epicenter distance. And the peak ground accelerations were 0.572 g, 0.63 g, and 1.065 g were recorded along 90 degrees, 360 degrees, and vertical components respectively. Notably, the vertical component exhibits a higher PGA compared to the horizontal component, which may be attributed to the presence of soft soil deposits in this area. The fault slip at this station exceeds 2.5 meters. The high amplitude portion of the ground motion record persisted by approximately 1 second. Despite the station's considerably distance from the epicenter, pulse-like ground motions were also observed for this ground motion with a pulse period of 3.6 seconds. A significant duration of less than 15 seconds was observed across all components of the ground motions, and the seismic recorded displayed at broad spectrum of frequencies. Now we'll see another ground motion record which was recorded at Guyang station. The Guyang seismic station, which is located approximately 137 kilometers from the epicenter. The peak ground accelerations were 0.042 g, 0.056 g, and 0.016 z along 90 degrees, 360 degrees, and vertical components respectively. The acceleration time history exhibits peaks of similar amplitude across the components despite the station's closer proximity to the epicenter compared to the Naipita and lower PGA were observed across all components, likely due to the greater distances from the fault. Further, pulse-like ground motions were not observed at this station. Importantly, the ground motion duration was notably prolonged, ranging from 150 to 220 seconds across all components. The narrowband frequency spectrum was identified at the peaks of the ground motion showed a similar amplitude across the components. Another station, which was the Chiang Mai in Thailand, which was located at an epicentral distance of 474 kilometers, and the peak ground accelerations were recorded 0.0092, which were very, very low values, 0.011 g and 0.0125 g that were located that was observed along 90 degrees, 360 degrees, and vertical components respectively. Now you can see the Fourier amplitude spectrum for Naipita station and Guyang station and Chiang Mai, Thailand station. Now we'll discuss about the response spectrum. So the response spectrum here, the response spectrum are drawn for spectral acceleration for Naipida station along three components: 90, 360, and vertical component. And Guyang station 90, 360, and vertical component. Similarly for Chiang Mai, Chiang Mai, Thailand station. In the comparison of the traditional time domain representation, the continuous wavelet transform offers a more nuanced graphical depiction of that captures the sequence of high amplitude frequency arrivals over time. So this transformation allows the visualization of how different frequencies, especially those with significant energy, contribute to the overall seismic response at various stages of the event. During an event, if the frequency of the ground motion is close to the natural frequency of the structure, it can cause substantial damage and further arrival of high amplitude waves with lower frequencies. Further, the economic loss, approximate economic loss was calculated for the Myanmar region due to this earthquake. Economic losses can also be correlated with the MMI scale in earthquake events. Higher MMI values generally correspond to the more extensive destruction and the consequently greater economic losses. So here you can see based on the literature, the correlation between the economic losses and the cost estimation. For MMI scale 1 to 3, the economic loss type is the minimal and the cost is approximately 0. And for MMI scale 4 to 5 ranges, the estimated cost is 1 to 10 millions. For 6 to 7 MMI scale intensity, the cost approximately 10 to $100 million. For 8 to 9, 100 to $1,000 million. For 10 to 12, the cost estimated is 1,000 to $10,000 million. Based on the previous study, a preliminary estimate of the economic loss resulted from the earthquake has been conducted. So this estimation is derived from the data collected at 70 seismic stations. The seismic intensity measured at the modified Mercalli intensity scale is sourced from USGS, and the economic loss calculated are based on the MMI scale with the corresponding relationship uh, is shown in the table in this slide. So as I explained earlier, so the total estimated economic loss from the earthquake is projected to be $5 billion, with cities such as Mandalay, Yamithin, and Sagaing anticipated to incur losses totaling approximately $1 billion. You can see the cities which has more economic losses along the Sagaing fault. So following are the conclusions, the seismic activity combined with the geological features of the region played a pivotal role in the extensive seismic damage to infrastructure. Portions of the Mandalay city and its structures are situated along the floodplain of the Ayarwadi river, which significantly increased the vulnerability of the buildings to liquefaction. Lack of technological advancements and non-enforcement of seismic building codes uh, heighten the seismic risk, resulting in substantial infrastructure damage, high casualty rates, and considerable economic losses. A widespread destruction in distant regions such as Thailand was a consequence of low frequency seismic waves generated by the Myanmar earthquake. Technological advancements such as geological information system, that is GIS, artificial intelligence, drone systems, automation, and IoT have proven invaluable in post earthquake damage assessment, as demonstrated in the aftermath of the Myanmar earthquake. So, some videos related to the Myanmar earthquakes are posted in the Acharya Gurukulam YouTube channel. So, please visit the channel to get more information related to the Myanmar 2025 Myanmar earthquake. Thank you. Jai Hind.